Okay, so let's do some examples with rational functions. So the first example I want to look at is, let's see if we can find the vertical asymptotes of a particular rational function. So find the vertical asymptotes of this particular function. So f of x is equal to 3x squared minus 14x minus 5 over 3x squared plus 8x minus 16. Okay, so remember, to find the vertical asymptotes, we want to determine where the denominator is equal to 0, right? Because it's where the function, where the rational function is undefined. That's going to be when the denominator is equal to 0. So what we want to do is we want to factor first both the numerator and denominator. And the reason why we want to do that, first of all, it'll make it easier to solve it, right? When we set it equal to 0, to figure out what those zeros are. And also, we want to factor the numerator so that we can make sure that there's no terms that are exactly the same that we can cancel out, right? Remember, that was the case if we had exactly the same factor in the numerator and denominator, then we would have an actual hole in our graph, right? So we do want to factor both. Okay, so this is just to remind you how to factor. You may not have done this in a while. So let's say we want to factor the numerator. So we have 3x squared minus 14x minus 5. Okay, one way of doing it is just guess and check, right? You could draw your two sets of parentheses, your two factors, and you could start guessing and checking. But another way, and I think the second way is a lot better, is if you use this technique. So if the coefficient of the x squared term is not a 1, in this case, it's a 3. If that's the case, what I do is I start by multiplying that 3 by the constant. You could think of it as a and c, so I'm multiplying a and c together. And when I do that, I'm going to get a negative 15. Okay, then what I want to do is I want to come up with two things when multiplied give me a negative 15, and when added, give me this middle term, the b term, of a negative 14. Well, in this case, I can think of two things, right? If I multiply negative 15 times a positive 1, if I multiply those together, I get negative 15. If I add them, I get negative 14. Great. So now what we do is we rewrite that middle term. So I rewrite negative 14x in terms of these two factors that I just found, the negative 15 and plus 1. So instead of negative 14x, I'm going to write this as negative 15x plus 1x, and then I still have a negative 5 there. So I just rewrote that middle term. Now what we can do is we can factor by grouping. So I group the first two terms together. I group the last two terms together. And I factor as much as I can out of that first group. So if I look at the first two terms, let's say 3x squared minus 15x, it looks like a 3x is common, right, to both terms. So I can pull out a 3x. And I'm left with x. So 3x times x gives me 3x squared. And what else? I guess a negative 5. And the goal usually is to factor whatever we can out of the second set of parentheses, the second group, so that we're left with an x minus 5. Well, since we already have an x minus 5, you can think of it as like we factored out a 1, right? You could also say we didn't do anything, but really clearly you can think of it as, well, we factored out a 1. Okay, why does that help us? Because now if you look at this, see how the x minus 5 is common to both terms? So I can factor it out front, right? I can pull that x minus 5 all the way out front. And I'm left with what? Well, x minus 5 times 3x gives me that first term. And then x minus 5 times a positive 1 will give me the second term. So this is my factorization. X minus 5 times 3x plus 1. Okay, I do the same thing for the denominator. So for the denominator, I had, let's see, I guess it was 3x squared plus 8x minus 16. Okay, so I'm going to multiply a times c. So 3 times negative 16, what's that? Negative 48. And now I want to think of two things. When multiplied, give me negative 48, and when added, give me a positive 8, because I want them to add to be that middle term, right? The b term, the b coefficient. So what two things when multiplied will give me negative 48 and added will give me positive 8? Well, if you think about this a little bit, right, it turns out that 12, a positive 12, and a negative 4 will work, right? If I multiply 12 times negative 4, that's negative 48, and 12 plus a negative 4 is a positive 8. So that works. So I'm going to rewrite that middle term, the 8x, in terms of these two factors, the 12 and negative 4. So I'll write it as plus 12x minus 4x, and then minus 16. Okay, factor by grouping again. So I grouped the first two terms. I grouped the last two terms. What you might want to do is put a plus there just to remind yourself that you're really adding, right? It's plus. I'm just putting parentheses to set aside those two terms. And now I factor as much as I can out of that first set of parentheses, out of the first factor. Well, it looks like I can take out a 3x. And I'm left with x plus 4. And then my goal is to factor something out of the second factor, right, the second set of parentheses, so that I'm left with x plus 4. Well, is there anything I can take out so I'm left with x plus 4? Yeah, if I factor out a negative 4, then I'm left with x, because negative 4 times x gives me negative 4x. And then plus 4, because negative 4 times positive 4 is a negative 16. Great. Again, this is good because now look at that x plus 4 is common to both terms, right? So it's common to both terms. So I can factor it out front and pull it out of both terms. It's out front. Now what am I left with? I'm left with a 3x, because this times 3x gives me that first term. And then I'm left with a negative 4, because that times negative 4 gives me the second term. Okay, so that would be the factorization. So this function, when it's fully factored, is going to be f of x is equal to, the numerator was x minus 5 times 3x plus 1 over, and denominator was x plus 4 times 3x minus 4. Okay, well, first of all, I don't have anything I can cancel, right? I can't cancel any of those factors. So there's no holes. I don't have to worry about any holes. So no holes. And now I can actually determine where the vertical asymptotes are. How do I do that? Remember, you set the denominator. So the denominator is x plus 4 times 3x minus 4. You set that equal to 0. I want to figure out what x values will make the denominator 0. So one possibility is x plus 4 is equal to 0, and that's going to give the solution x is negative 4. And the other possibility is 3x minus 4 is equal to 0. So then if I solve for x here, I get 3x is equal to 4 divided by 3. Looks like x is equal to 4/3. So that means I have a vertical asymptote at two locations, right? The line x equals negative 4. That vertical line is a vertical asymptote, and also the line x equals 4/3 is a vertical asymptote. Okay, let me plot this graph and show you this. Okay, so here is the graph of that rational function. And if you notice here, at x equals -4, that's this vertical line that goes straight up. So right along here. Well, if I approach -4 from the left, the graph is going to positive infinity. If I approach -4 from the right, the graph is going to negative infinity. So definitely x equals -4 is a vertical asymptote, like we found. And then this one over here, right, which is right, looks like a little bit past 1. And actually, yeah, we found it was 4/3, right? So that's like 1 1/3. So right around x equals 1 1/3, that vertical line is also a vertical asymptote because the function is approaching either infinity or negative infinity. In this case, if I approach from the left, it's approaching positive infinity. If I approach 4/3 from the right, it's approaching negative infinity. So those are my two vertical asymptotes. So here's actually maybe a better picture of this where I actually plotted those vertical lines. So I have a dashed line again at x equals -4 and a dashed line at x equals 4/3. And those are both vertical asymptotes because the function is either going to positive infinity or negative infinity as it approaches from either of the sides. Okay, let's do another example. Okay, so in this example, we want to find the vertical asymptotes again, but of a different rational function. So find the vertical asymptotes of this function. Say a of x is equal to x squared plus 2x minus 3 over x squared minus 1. Okay, so just like before, we need to factor, right, the numerator and denominator so we can see what's going on here. So let's start with the numerator. So I have x squared plus 2x minus 3. Well, if the coefficient of the x squared is a 1, that's the nice case where we can immediately draw our two sets of parentheses, right, our two factors. And because the only way we can get x squared is if I multiply x times x. And then if we can think of two things when multiplied that gives us -3 and added will give us a +2, then we will have factored it. Well, can we think of two things when multiplied give us -3 and added give us +2? Yeah, a +3 and a -1 will work, right? If I do a +3 and then a -1. Okay. And then the second, the denominator, so x squared minus 1, this is just a difference of squares, right? Remember, let me go over here to remind you this. Remember, if you have a squared minus b squared, to factor that, it's going to factor into a plus b times a minus b, right? If you FOIL that back out, you're going to find that you get a squared minus b squared. So that's something that you should just remember because it comes up a lot. So x squared minus 1 is the same thing as x squared minus 1 squared. So this factors into x plus 1 times x minus 1. Okay, and again, if you want to make sure that you're correct, just multiply this back out, FOIL it back out, and make sure that you end up with x squared minus 1. All right, so therefore, a, that function, right, is a function of x. We can now write in factored form, it's going to be x plus 3 times x minus 1, that's in the numerator, divided by x plus 1 times x minus 1 in the denominator. Okay, now here, normally you would think, okay, it looks like I have vertical asymptotes where the denominator is 0, right? So where's the denominator going to be 0? The denominator is going to be 0 when x is -1 and when x is +1. But it turns out the vertical line x equals 1 is actually not a vertical asymptote because these two factors of x minus 1 can cancel, right? These actually cancel. The function itself is definitely undefined when x equals 1, but it's not a vertical asymptote because those two factors cancel. So what does that mean? It means that you have a hole in the graph. In graph at x equals 1. Why a hole? Because it's not defined. At that one particular location, it's not defined. So then it simplifies it quite a bit, right? So now this function is simply x plus 3 over x plus 1, which is exactly the same as the original function, except we have to remember that we have a hole at x equals 1. But now I can set the denominator equal to 0. And when is that equal to 0? Well, it's equal to 0 when x is -1. So I have a vertical asymptote and the vertical line itself is x equals -1. That would be the equation of that line. Okay, let me plot this to show you what this particular function looks like. Okay, so this is the graph of the rational function that we just looked at. And notice that there is a vertical asymptote at x equals -1, right? So we have a vertical line, x equals -1, that's our vertical asymptote. But at x equals 1, there is no vertical asymptote. There is, however, a hole here, and you can't see it well because it's just a single point that's taken out. So Desmos doesn't even show you that. But in reality, let me see if I can annotate this. In reality, there is going to be a hole right there. So that one little point, the point 1 comma 2, actually doesn't exist, right? So there will be a hole there. So vertical asymptote at x equals -1, and then a hole at x equals 1. And how do you know that there's a hole? Because those two factors cancel. So whenever you can cancel a factor, so x equal 1 made both the numerator and denominator both 0, therefore there was a hole there. So it's undefined there, but it doesn't lead to a vertical asymptote. Okay. Let's talk now how to find horizontal asymptotes. So let me go back to the iPad. Okay, so to find horizontal asymptotes, we have to look at the long run behavior of the rational function. So we have to look at the long run behavior of the rational function. Which depends on the ratio of the leading terms of the numerator and denominator functions. So which depends on the leading actually, let me back that up for a second. Depends on the ratio of the leading terms of the numerator and denominator functions. Okay, so there's going to be three cases. So case one, let me move this up a little bit. Case one would be a case where the degree of the denominator is greater than the degree of the numerator. Okay, so let me give you an example. For example, let's say we have a rational function and it's 2x minus 4, right? So that's our polynomial in the numerator over, say, x squared minus 3. That's our polynomial in the denominator. Well, the long-run behavior only depends on the long-run behavior of the rational function, which only depends on the ratio of the leading term in the numerator over the leading term in the denominator. So for long-run behavior, this function is going to look like, I'll do like approximately, it's just going to look like 2x, because that's the leading term of the numerator, divided by x squared, right? Because that would be the leading term of the denominator. And we can simplify that, right? We can cancel out on x. So this is equal to 2 over x. Okay, so what happens now? Let's think about that function 2 over x. As x goes to negative infinity, what's happening to 2 over x? Well, as x gets, very, very, very negative, so negative 100, negative a million, negative a trillion, and so on, that number is it's still going to be negative, but it's getting closer and closer and closer to 0, right? It's going to be a very, very small negative number. So we can say as x approaches negative infinity, that function approaches 0. So that means our rational function is also going to approach 0, right? Because it only depends on the leading term of the numerator divided by the leading term of the denominator, which is 2 over x. And then if we go the other way, so as the input, as x gets really, really large, well, what happens? Think of like 2 over 100, 2 over 1,000, 2 over a million, 2 over a billion. Again, the function is going towards 0. So what does that mean? It means that we have a horizontal asymptote of y equals 0. Of y equals 0, because the function is approaching that value, y equals 0. Okay, actually, let me stop right here and show you this on Desmos. Okay, so here's a graph of that rational function, 2x minus 4 over x squared minus 3, right? So that was right here, 2x minus 4 over x squared minus 3. And notice a couple of things. First of all, we weren't specifically looking at vertical asymptotes, but in this case, there's 2 vertical asymptotes, right? In fact, if you set that denominator equal to 0 and solve for it, you're going to get x equals the square root of 3 and x equals negative square root of 3. So we have this line right here is x equals negative square root of 3, and this is x equals positive square root of 3. right? And they're vertical asymptotes because the function is blowing up as it approaches those values, either going to positive infinity or negative infinity. And then as the input gets really, really large or really, really small, what's happening? Well, the rational function is approaching zero. So right at zero, and it's hard to see, but I put a dashed line in there, that is our horizontal asymptote. An asymptote means it's approaching it, right? Something, you say something is asymptotic to a curve, it means it gets closer and closer and closer to that particular, in this case, that particular horizontal line. So it's asymptotic to that line. So that's our horizontal asymptote, which is basically the x-axis, which has the equation y equals 0, right? It's a horizontal line, so it's y equals 0. Okay, let's look at case 2. So that was case 1, where the denominator is greater than the numerator. You're always going to have a horizontal asymptote of y equals 0 if that's the case. Okay, so here's the next case, case 2. Suppose that the degree of the denominator is less than the degree of the numerator. So degree of denominator is less than the degree of the numerator. And I'll do a couple of examples in this case. So let's say my first example, I have x squared plus 4x minus 5 over, say, 3x plus 6. So in this case, the degree of the denominator is 1, right? It's a just linear function, so it's a first degree, or the highest exponent is a 1, is another way of thinking about it, of any of the terms. And the degree of the numerator is a 2, right? So the degree of the denominator is less than the degree of the numerator. Or you could also say the degree of the numerator is larger than the degree of the denominator. So that means for long-run behavior of this rational function, really I should give this a name, right? Let's call it f of x is equal to that. So the long-run behavior only depends on the ratio of the leading terms. So I'll say f of x is approximately equal to x squared over 3x, right? X squared is the leading term for the numerator, and 3x is the leading term, the largest term in the denominator. And then, of course, I can simplify this. This is simply equal to x over 3, right? Or 1/3 x over 3. Well, what happens now as x goes to negative infinity or x goes to positive infinity? This function since this is, think of it as almost like it's like an identity function, right? That's multiplied by 1/3. It's like a line. So it's definitely not approaching any particular value, right? In this case, as x goes to negative infinity, x over 3 also goes to negative infinity. And as x goes to positive infinity, x over 3 goes to positive infinity. So in this case, you would say that there's no horizontal asymptote. Right? Because the function doesn't approach any constant value. It just blows up. So anytime that the degree of the denominator is less than the degree of the numerator, or vice versa, you could say the degree of the numerator is larger than the degree of the denominator, then there will not be a horizontal asymptote. Okay. Another example would be, let's say we have this instead. So let's say our rational function was 3x to the 5th minus 5x plus 1 over x plus 2. So if I'm just looking at long run behavior, I only need to look at, again, the ratio of the leading term. So f of x looks like, I'll say approximately, 3x to the fifth over x. But that's equal to 3x to the fourth. Well, so in this case, what happens as the input gets really, really small or really, really large, again, f of x is going to blow up. And in fact, in this case, since I have 3x to the fourth, in both cases, if x gets really, really small as it heads towards negative infinity or really, really large towards positive infinity, the function is going to go towards infinity, right? It's going to approach infinity. So again, we'd say that there's no horizontal asymptote. So anytime the degree of the denominator is less than the degree of the numerator, right? You just have to look at the leading terms. Then there's no horizontal asymptote. Let me plot these two functions just to show you what these look like. Okay, so this was that first function. So it was x squared plus 4x minus 5 over 3x plus 6. So again, the degree of the denominator was less than the degree of the numerator. And what happens? Well, as the input, as x gets larger and larger and larger, the function is also growing towards infinity. It's not approaching some constant number. So there is no horizontal asymptote. And as x gets really, really small, it's also going towards negative infinity, right? It's not approaching any constant number. In fact, if you look at this carefully, remember we found that when we simplified it, we got x over 3. If I plot x over 3, that's really what it's going to be approaching in the long run. So let me plot x divided by 3. Let me get dashed. So you can see in the long run, this must like go back on it and it approaches x minus 3. I can zoom out actually and see it better. So as x gets really, really large or really, really small, it's approaching that line 1/3 x, right? Or x minus 3. Okay, and then for the second function, let's show that that also doesn't have a horizontal asymptote. That was, what was it? 3x to the fifth minus 5x, right, plus 1 divided by x plus 2. I guess I'll have to zoom in. But clearly you can see that the function does not approach some constant value. It's as x gets larger and larger and larger, it's blowing up. As x gets smaller, it's going towards negative infinity. Okay, so there's no horizontal asymptote in this case. All right. There's one more case, so let's do that last case. Okay, now this last case, so case 3, oh, let me go to black. This may be the most interesting one. This is when the degree of the denominator equals the degree of the numerator. So degree of denominator equals the degree of the numerator. So an example of that would be the following. Let's say I have a rational function f of x is equal to 2x squared plus 2x minus 5 over, say, x squared minus x plus 3. So if I look at the long run behavior, again, remember, it only depends on the leading term of the numerator, which is 2x squared, over the leading term of the denominator. But that just simplifies to 2, right? Because in this case, the degree of the numerator was 2, degree of the denominator is 2, they're equal. And I can just look at the ratio, 2 over 1, which is 2. So what this means is that as x approaches negative infinity, or as x approaches positive infinity, what's happening with this rational function? It's approaching the value 2. So it's approaching that constant, right? So basically, in this case, there is a horizontal asymptote, and it's the line y equals 2. So there's a horizontal asymptote, and it's the line y equals 2. So the function is getting closer and closer and closer to 2 as x gets either really, really big or really, really small. All right. Actually, let me plot this for you just so we have it. Okay, so this is a graph of that function. And notice that, and I plotted the line y equals 2 just to show you this. Notice that as x gets really, really large, then the function, which is the green graph here, is getting closer and closer to 2. So it's approaching 2. And then over here, and actually it's from above, but that's okay. And then here, when x gets really, really small, it's approaching 2 again. It happens to be from below, but it's still approaching 2. So that line, y equals 2, is a horizontal asymptote. Now, one interesting thing is it looks like there should be some vertical asymptotes, right? Like where the denominator is equal to 0. But it turns out if you try and solve that, there's no real no real x's that make that denominator 0. So in this case, there's no vertical asymptotes either. But the thing we were just looking at was the horizontal asymptotes. Okay, let me do some more problems where we have to pick out a bunch of different things. So I'll do one more problem where we look at vertical and horizontal asymptotes. Then we'll talk about intercepts, right? Intercepts are similar to what we did earlier with polynomials. And then we'll kind of combine everything together. Okay, so let's try this problem. So let's say we want to find the vertical and horizontal asymptotes of this function. I'll call it w. W as a function of x equals x minus 1 times x plus 3 times x minus 5 over x plus 2 squared, and then x minus 4. Okay, so first of all, there's no factors that are the same in the numerator and denominator, right? So there's no x that makes both the numerator and denominator 0. Right? If there's no two factors that are the same, there's no x that will make both the numerator and denominator 0. Therefore, what does that tell us? It tells us that there's no holes. So it's a good place to start. So there's no holes because we can't cancel anything, right? So no holes. Now, for the vertical asymptotes, Well, to find those, I have to set the denominator equal to 0. So that's going to give two solutions in this case, right? One possibility is that x plus 2 squared is equal to 0, and that's going to give the solution x equals -2. Actually, it gives a double solution, right? X equals -2, x equals -2. And I'll explain what that means in terms of the graph later if we have a squared term in our exponent, if we have a 2 in our exponent. And then the other possibility is that if x, let's see, x minus 4 is equal to 0, then x is equal to 4. So when x equals -2 or x equals 4, that makes the denominator 0. Therefore, we have two vertical asymptotes, right? We have the line x equals -2. That is a vertical asymptote. And then the line x equals 4. That's also a vertical asymptote. Okay, what about horizontal asymptotes? Well, what's the leading term of the numerator, right? Because remember, to figure out horizontal asymptotes, I want to look at long run behavior. And that only depends on, so right, Wx is approximately equal to the leading term of the numerator. So if you think about this, right, if I were to expand this out, my first term would be x times x times x, right? Because those are the three largest terms of each of those factors. So it looks like it's going to be x cubed over, and then in the bottom, well, if I square this term, x plus 2 squared, I'm going to get an x squared. X squared times x is also x cubed. And this just simplifies to 1, right? Those two, the degree of the numerator and degree of the denominator are the same. So it's just going to be the ratio of the coefficients, which is 1. So in this case, I must have a horizontal asymptote, and that line is going to be y is equal to 1. Okay, let me plot this to see what this looks like. Make sure we're correct. Okay, so here's that function we were just working with. And notice that the vertical asymptotes were just as we thought, right? So we have one at x equals -2. In fact, in this case, as I approach -2 from the left and from the right, the function is going to -infinity in both cases. And then we have one at x equals 4, so another vertical asymptote at x equals 4. In this case, if I approach 4 from the left, it goes to positive infinity. If I approach 4 from the right, it goes to -infinity. I'll explain why that's true in a little bit. It turns out it depends on the exponent of that factor. Remember the x equals -2 vertical asymptote? That came from the factor x plus 2 squared. And it turns out the squared, right, the 2 in the exponent, tells us that the graph is going to go in the same direction as I approach. In this case, they're both going to -infinity. They could either be both going to positive infinity or both going to -infinity. In this case, they're both going to -infinity. And it comes from the fact that that factor was squared. And then the other factor, the x equals 4, that vertical asymptote, that came from the factor x minus 4, right, to the 1 power. In that case, as you approach 4 from the left and right, one side is going to go to positive infinity, the other side is going to go to -infinity. Okay, but I'll explain that more carefully in a few minutes. And then for the horizontal asymptote, remember the degree of the numerator, it was this function right here. The degree of the numerator was x cubed. The degree of the denominator was, again, x cubed, right, 1x cubed. So they canceled and you get 1 over 1, which is 1. And that is our horizontal asymptote, y equals 1. So that line right there. So as the input gets larger and larger and larger, this function approaches 1. And as the input gets smaller and smaller and smaller, the function again approaches 1. So we have a horizontal asymptote at y equals 1. Okay, let's talk a little bit about how to find the intercepts of a rational function. Okay, now let's talk about the intercepts of rational functions. So, intercepts of rational functions. So, vertical intercept is exactly what we've seen for any type of function, right? If we set the input equal to 0, typically the input we call x. So if we set x equal to 0 and we solve for the output, right, which we typically call y, solve for y, that's going to give us the vertical intercept. So let me write that down. So a vertical intercept will occur when the input is 0. So I'll say set x equal to 0 and solve for y. Even though you might call the input something other than x and you might call the output something other than y. But in general, let's say we call the input x and the output y. So you set x equal to 0 and you solve for y, just like we've been doing for all the different types of functions. Okay. Now for horizontal intercepts. So a rational function will have horizontal intercepts at inputs that cause the output to be 0. Unless the input corresponds to a whole. Right? Then it wouldn't be a horizontal intercept, it would just be a whole, right? So anytime you can cancel factors from the numerator and denominator, if you have the same factor, then you just have a whole at where that factor equals 0. So you don't have a vertical asymptote, you don't have a horizontal intercept. It would just be a whole in that case. All right, so another way of saying this and again, this is really nothing new. You can think of this as setting the output, so y equal to 0, and solving for x. Solving for the input. Okay. After you've canceled any potential factors that are the same, then you would set y equal to 0 and solve for x. So what does that really mean? It means ultimately to find horizontal intercepts, all you have to do is set the numerator of the rational function equal to 0 and solve. So we set the numerator, and I'll explain this in examples in a few seconds, equal to 0. and solve for the input, which I'll call x. In general, we call x, right? Okay, so what does this all mean? Let's do an example. So here's an example. Let's say I have, this is my rational function. K of x is equal to 2x squared minus 3x minus 20 all over x minus 5. Okay, well, first thing I need to do is I need to factor that numerator, right? We really want everything in factored form so we can easily see what's going on here, and if we need to cancel terms or whatnot. So I need to factor that numerator. So let me do that on the side over here. So I have 2x squared minus 3x minus 20, and I want to factor it. So remember, if the coefficient of the x squared term is not a 1, then the way to factor this is to multiply that coefficient, right? Usually we call that the a, times the constant, which we call the c. So if I multiply 2 times negative 20, I get negative 40. Then I want to think of two things when multiplied give me negative 40, and when added will give me that middle term, the b term, the coefficient of the x, of a negative 3. So two things when multiplied give me negative 40, and added give me negative 3. Sometimes you have to think about this a little bit. Well, I guess negative 8 and positive 5 will work, right? So now I rewrite this middle term, the negative 3x, in terms of these two factors. So now this becomes 2x squared minus 8x plus 5x minus 20. And then once we have the four terms there, we factor by grouping, right? So I group the first two terms, I group the last two terms. What's the largest thing I can pull out of the first group? Well, it looks like the largest thing I can take out is 2x. And I'm left with x minus, let's see, I guess it's 4, right? Now, I would like to factor something out of the second group so that I'm also left with x minus 4. Is there something I can take out? Yeah, if I take out a positive 5, I guess, right? So if I pull out a positive 5, I'm left with x minus 4. So now this x minus 4 is common to both terms, so I can factor it out front, pull it all the way out front. And I'm left with 2x, right? Because if I multiply x minus 4 times 2x, I get that first term, and then plus 5. If I multiply x minus 4 times 5, I get this second term right here. So x minus 4 times 2x gives me the first term, and then x minus 4 times 5 gives me that second term there. Okay, so that's the factorization. So that means k of x, I'll just write it in factored form now. It can be written as x minus 4 over 2x plus 5 all over x minus 5. Okay. Are there any factors that we can cancel? No, in this case, right, no factors are the same, so I can't cancel anything. So I know that there's no holes. Now let's try and find the intercepts, right? This problem asks us to find the intercepts. So I'll start with the vertical one because that's always the easier. So the vertical intercept. Well, to find that, I need to set the x equal to 0 and solve for k, right? Solve for the output. So I need to plug in 0 for x. So wherever I have an x, I'm plugging in 0. Okay, so now if we work this out, well, 0 minus 4 is a negative 4. 2 times 0 is 0, right? 0 plus 5 is 5. So negative 4 times positive 5, it looks like it's a negative 20. And then 0 minus 5 is a negative 5. And that simplifies to 4. So it looks like our vertical intercept is the ordered pair at the point 0, 4, right? That's where it would pass through the vertical axis, or in this case, the k-axis, which we usually call the y-axis. I'm just using different variables so you get familiar with the fact that it doesn't always have to be x and y, right? In this case, we're using x and k. It can have many different names. Okay, now for the horizontal intercepts, so horizontal intercepts. In general, we set the entire function equal to 0, right? We force the output to be 0, k to be 0. And I solve for x. But what I can do first is I can multiply both sides by x minus 5 just to clear it out. So if I multiply the left-hand side by x minus 5, and then the right-hand side by x minus 5, what's going to happen? Well, the x minus 5s cancel on the left-hand side, right? And I just get x minus 4 times 2x plus 5 equals, and then 0 times x minus 5, well, 0 times anything is 0. So this is why we said that ultimately to test for or to find the horizontal intercepts, you really only need to set the numerator equal to 0. Because then you can just multiply both sides by the denominator, and 0 times that denominator is going to give you 0. So the denominator isn't a factor. It's just the numerator equals 0 is all you have to use to test or to find the horizontal intercepts. So now let's solve this. So one possibility is x minus 4 is equal to 0. And that's going to give the solution x is equal to 4. And then the other possibility is 2x plus 5 is equal to 0. And if I solve this, so I need to subtract 5. So I have 2x equals negative 5 divided by 2. That's going to give the solution x equals negative 5 halves. So therefore, I'm running out of room here. Let me just do it a little bit over here. My horizontal intercepts are going to be the points 4, 0 and negative 5 halves, 0. So that's where the rational function is going to pass through the x-axis, right? They're my horizontal intercepts. It's where the graph of that rational function passes through the x-axis. Okay. Here, let me graph this real quick to show you that. Okay, so here is that function that we just looked at, 2x squared minus 3x minus 20 over x minus 5. Remember, we factored the numerator, so it became x minus 4 times 2x plus 5 over x minus 5. And when we plugged in 0 for x, we found the vertical intercept, so that was right here at 0, 4, right? So that makes sense. And then when we set the numerator equal to 0 and solve for x, we found that x equals 4, so that's one of the horizontal intercepts, 4, 0. And then the other one was at negative 5 halves, so negative 2.5, right, is 5 halves, 0. And actually, if you look at this, notice this also has a vertical asymptote, right? Because if we look at the denominator here, when is this equal to 0? It's equal to 0, like when is it undefined? When x equals 5. So actually, let me plot that. So x equals 5. That's going to be a vertical asymptote. So as this function, as the x input gets closer and closer to 5, it looks like the function is going to negative infinity, right? So we actually have a vertical asymptote at x equals 5. Okay, let me describe now the behavior of the graphs near the vertical asymptotes. We talked a little bit about this a couple of graphs ago, but let me do this more carefully. Okay, so behavior of graphs near vertical asymptotes. It depends on the power of the factors in the denominator. Remember, to find the vertical asymptotes, we set the denominator equal to 0. So we set each factor equal to 0 and we solve for x, right? Well, it turns out how the graph looks, the shape of the graph, depends on the power of those factors. By power, we mean the exponent, right? And the only two that we're going to deal with in this class is whether it's raised to the 1 power or whether it's squared, whether it's raised to the 2nd power. So if the factor is raised to the 1 power, so if it's basically, I'll write it this way, x minus something to the 1 power, then the graph will look similar to our reciprocal functions. So, and it depends on whether it's flipped or not. It's either going to look like this, 1 over x, which remember looks like this, or it could be flipped. So it might look like negative 1 over x. So there would be a vertical reflection in that case. So it could look like this. Okay, so what do I mean by that? What are we getting at here? Well, what I mean is if the power is a 1, okay, so if the power is a 1, then near that vertical asymptote, if you approach from one side, like if I approach from the left here, one side is going to go either to, in this case, it goes to negative infinity. In this example, it's going to positive infinity. And then the other side will do the opposite. So if I approach from the right, this one's going to positive infinity. And over here, this one's going to negative infinity. But it's doing the opposite. One side is approaching negative infinity. The other side is approaching positive infinity. That will always happen near a vertical asymptote if the power is a 1. Now, if the power is a 2, so if the factor is something like this, x minus a squared, then the graph is going to look similar to a reciprocal squared function. So it looks similar to a reciprocal squared function. So in other words, one possibility is the graph will look like this. So if I have 1 over x squared, remember that looks like this. Or it could be flipped again. So it could look like negative 1 over x squared, which looks like this. And again, what are we saying here? Well, we're saying that if that factor in the denominator is squared, if it has a 2 in the exponent, then if you look near that vertical asymptote, as you approach from the left and from the right, the function is going to do the same thing on both sides. So in this case, they're both going towards positive infinity. And on this example, they're both going towards negative infinity. So they're going to do the same thing. They're both going to go in the same direction if it's a squared. If it's a 1, if it's a linear term, they're going to go in opposite directions. If it's squared, they're going to go in the same direction. Okay, and then the other thing is what happens near the horizontal intercepts. And that's similar to what we saw with polynomials. Okay, so I'll write that at the bottom here. So the shape, actually, let me move this a little bit for you. Okay, so the shape of the graphs, remember these are of the rational functions, right? Shape of the graphs of the rational functions near the intercepts, I'll say horizontal intercepts, is similar to what we saw with the polynomials. And remember what happened in that case, right? If the exponent on the factor was a 1, it looked like a line near the intercept. If the exponent was a 2 on the factor for the x-intercept, it looked like, or the 0, remember sometimes they call it a 0 or a root, it looked like a parabola, it looked like a quadratic function. And if it was a 3, it looked like a cubic function, right near that root. So that's going to be the same with the rational functions as well. Okay, so let's do an example. Let's see if we can sketch. Let me put up a new page here. Let's say we want to sketch a graph and then we'll check it later with Desmos, but sketch a graph of this rational function. So f of x is equal to x plus 3 times x minus 4 over x plus 1 squared times x minus 2. Okay, so what's going on here? First of all, let's figure out, let's do the asymptotes first. So are there any vertical asymptotes? Well, remember, how do I find vertical asymptotes? I have to see where the denominator is equal to 0. So I could set my denominator equal to 0. And solve for x. And if you do that, and you can see here that you can just pick this out, one vertical asymptote is going to be at the point or at the line x equals -1, and the other one will be the line x equals 2. Okay, so those are our vertical asymptotes, right? It come from setting the denominator equal to 0. All right, horizontal asymptotes. How do I find those? Well, I have to look at the leading term, the ratio of the leading term of the numerator to the leading term of the denominator. If you look at this function, well, if I were to expand this out, it looks like the leading term of the numerator is going to be x times x, so x squared. And of the denominator, well, I have x plus 1 squared, so that's going to give me x squared times x. It looks like x cubed, right? So the function, when we're talking about horizontal asymptotes, we're only considering long-run behavior. So we just need to look at the ratio of the leading term of the numerator to the leading term of the denominator. The leading term of the numerator, it looks like it's x squared. Of the denominator, it's x cubed, but this is the same as 1 over x, right? Because the x squared will cancel. So is there a horizontal asymptote? Yes, because as x gets really, really large, right, as it approaches positive infinity, or really, really small, approaches negative infinity, what is this function approaching? It's approaching 0, right? Remember, if the degree of the denominator is larger than the degree of the numerator, then you're always going to have a horizontal asymptote, and it's going to be that line y equals 0. Okay, so we know that. What else do we know? What about intercepts? So let's do vertical intercept first. So vertical intercepts, or intercept is only one of them, right? How do I find that? Well, I plug in 0, right? I set x equal to 0 and I solve for the output, solve for y. So in this case, f of 0 is going to be, let's see, I guess it was 0 plus 3 times 0 minus 4 over 0 plus 1 squared over 0 minus 2. So if I work this out, let's see, 0 plus 3 is 3. 3 times -4 is -12. And then 1 squared is 1. 1 times -2 is -2. So it looks like that's a +6. So it looks like I'm going to have a vertical intercept at the point 0, 6. And then finally, horizontal intercepts. That's when I set the numerator equal to 0 and solve, right? Or you could say set the whole thing equal to 0, but then you can multiply both sides by the denominator, and that's going to clear it out. So ultimately, you're just going to set the numerator equal to 0. Because we know already, by the way, let me go back to the top here. Since I can't cancel any of these factors, I know immediately that there's no holes. So don't have to worry about any holes. So if I want to find the horizontal intercepts, I need to set the whole thing equal to 0, but that's the same as saying set the numerator equal to 0. So I just need to set x plus 3 times x minus 4 equal to 0. And if I solve for those values, well, one possibility is x plus 3 is 0. The other one is x minus 4 is 0. So this one will give me x equals -3. And this one will give me x is equal to +4. So it looks like I have a horizontal intercept at -3, 0, right at that point, and then another one at 4, 0. Okay, so let's put this all together and see if we can at least get a sketch. It's not going to be great, but let's see if we can get at least a sketch of this graph. So I'll do it on a new page. Okay, so again, remember that the function was f of x was x plus 3 times x minus 4 over x plus 1 squared times x minus 2. Okay, so here is my Cartesian coordinate system. I need to go a little higher here. All right, now what did we find? We found that there was a vertical asymptote at x equals vertical asymptote at x equals -1 and x equals 2. Right, so I can draw that in here. So this is the one at -1. And then it also had one at 2, right? So something like this. So you should just do a dashed line, right, for the vertical asymptote. Okay, what else do we know? Well, we know that there was a horizontal asymptote of y equals 0. So we know it's got to approach y equals 0 is just the x-axis, right? So it's got to approach the x-axis as the input gets really, really large or really, really small. Okay, what else do we know? We know that there was a vertical intercept at the point 0, 6. So somehow it has to pass through this point right here, 0, 6. And then there was horizontal intercepts at the points -3, 0 and 4, 0. Okay, so horizontal intercepts at -3, 0, so that's right here, and then 4, 0. Okay, so what does this function look like? Well, I know that the graph has to pass through that vertical intercept of 0, 6. And I know that it can't go through the x-axis in between those two vertical asymptotes, right? Because there's no horizontal intercept there. So the graph must look, it must somehow go up, right? It must look something like this. Pass through, and then it's got to turn around somewhere and then go up again. How do I know that? Because I know it can't pass through anywhere down here, right? It can't pass anywhere through here because there are no horizontal intercepts between -1 and 2. Remember, they were at -3, 0 and 4, 0. So it must go up. Okay, now I also know that when it passes through these horizontal intercepts, it's going to look like a line. How do I know that? Because look at these two factors here in the numerator. They're both to the 1 power. Remember, if they're to the 1 power, it's going to look like a line. So the function on the left side, I guess it's going to do something like this, right? It's also going to shoot up to positive infinity there. It's got to somehow go through here and then turn somewhere, and then it's got to approach 0, right? Because remember, there's a horizontal asymptote at 0. So when x gets really, really small, this has got to get closer and closer and closer to 0. How do I know that both sides approach positive infinity as you get closer and closer and closer to that vertical asymptote at x equals -1? See how this side, the right side, goes to positive infinity and the left side goes to positive infinity? How do I know that? Because of this 2 on this factor, right? The x minus 1 or x equals -1 vertical asymptote comes from this factor, x plus 1 squared, and the squared tells you that it has to look like a reciprocal squared function. Basically, the function is either both going to go to positive infinity or both go to negative infinity. In this case, they both have to go to positive infinity. All right, now what about the other side? How does the graph pass through the point 4, 0? Well, it has to look like a line, right, when it passes through. Again, that's because of the 1 right here, right? So it has to look like a line. And because the x minus 2 on the bottom has a 1 as an exponent, remember the vertical asymptote at x equals 2, so this dashed line, x equals 2, that, since there's a 1 there, if I approach from one side, it goes to positive infinity, and the other side has to do the opposite. So in this case, it must go to negative infinity, somehow pass through 4, 0, and it's got to look like a line. Then as x gets really, really big, it's got to get closer to 0, so it must turn at some point and then approach 0. Now, it's really difficult to figure out exactly like where these things turn, and then you need more advanced math. You need some calculus to figure that out, but we should have the basics correct, okay? So let me plot this on decimals and see, let's see how close we were. Okay, so this is the graph. Actually, that's not bad, right? So we know, first of all, we know that it had a vertical intercept at 0, 6, so we have that. It had a horizontal intercept at -3, 0, so we have that one here, and then at 4, 0, so that's here. There was a vertical asymptote at x equals -1, and because that factor in the denominator was squared, we know that both of these functions go in the same direction. In this case, they both go towards positive infinity. Again, how did I know that they didn't go this way towards negative infinity? Because I know that the function had to pass through this point right here, through 0, 6. And since there was no horizontal intercepts between here, between -1 and 2, I know it couldn't have gone, through here. So it must have turned at some point. So it must look something like that, right? If it passes through, it had to turn at some point. It happens to be right here at 1. So definitely had a vertical asymptote at x equals -1. And again, since it was squared, the function both goes towards positive infinity. There's another vertical asymptote at x equals 2, and that comes from the x minus 2 factor. And since that exponent was a 1, one side goes to positive infinity and the other side does the opposite. So in this case, since we knew that this side had to go to positive infinity, that meant that side had to go to negative infinity. Then it's going to pass through 4. It's going to look linear. So if you zoom in there, it looks like a line going through 4. And then eventually it's going to like turn back because as x gets really, really large, it has to get closer and closer to 0 because we had a horizontal asymptote at y equals 0, or of y equals 0, that horizontal line. And same thing as x gets really, really small, right? It went through 3. It looked like a line going through 3 if you zoomed in. And then it turns somewhere and then it gets closer and closer and closer to 0 because of that horizontal asymptote of y equals 0. So we actually did a pretty good job. If you get something even close to this, that's great because it's really difficult to get it exact, right? Unless you know a lot more math. Okay, let me do this now. Let me give you a graph and let's try and come up with the actual function. Actually, we'll do a few problems like this. So now I'll do the opposite. I'll give you a graph and we'll try and come up with the rational function that describes that graph. Okay, so let me pause this and create a graph for you. Okay, so here's a graph of a rational function, and given this graph, we want to write down the equation of that function, right? We want to actually come up with the equation. So let's think about this. Actually, let me annotate this. I'll just do text, I guess, here. Okay, so what do I know? Well, if you look at this, it definitely looks like we have a vertical asymptote at x equals -3. So I'll say vertical asymptote, and there's one at x equals -3. So that must come from the factor x plus 3, right? And that factor would be in the denominator. Because if I solve x plus 3 equals 0, I'm going to get x equals -3. So it comes from the factor, right here, comes from the factor x plus 3. And it's in the denominator, right? Because it's in a vertical asymptote. And what is the exponent? Well, because one side is approaching infinity, the other side is approaching -infinity, the exponent must just be a 1, right? So I can leave it like that. Okay, the other vertical asymptote. Looks like we have another one at x equals 4. So that comes from the factor, let me write over here so I have more room. So x equals 4. That comes from another factor in the denominator. And what is that factor? It's x minus 4. And what is the exponent? Well, again, since one side of the function is approaching positive infinity, the other side is approaching negative infinity, right? They're going opposite directions. It's got to be a 1 again. Remember, it's either going to be a 1 or a 2. If you go from both sides and they both approach infinity or both approach negative infinity, then it'll be a 2. But if they're opposite, if one goes to negative infinity, the other goes to positive infinity, it'll be a 1, right? So in this case, it's just a 1. Okay, what else do we know? We know that there is a, let's see, there's a vertical intercept of 0, 1, right? That's where it's passing through the y-axis, the vertical axis. So there's a vertical intercept right there at 0, 1. And it looks like there's one horizontal intercept at -3, 0. Okay, so that's right here, right? It's the only place it's passing through the x-axis, -3, 0. So where does that come from? Well, that factor had to be in the numerator. So this comes from the factor x minus 3, right, in the numerator. And what is the exponent? Well, that depends on what this looks like. Well, if you zoom in on this, so if I zoom in, oh, I gotta get out of those. If I zoom in on this, it looks like a line going through, right? It just looks linear. It looks like a line going through. So that means the exponent here on the x minus 3 must be a 1, right? If it looked like a parabola, if it just touched and bounced off, then it would be a 2. And if it looked like a cubic where it gets flat and it goes back down, then it'd be a 3. Remember, we're only going to deal with 1, 2, or 3 for these horizontal intercepts. Okay, so let me put all this information together. All right, let me go back to the iPad to finish this. Okay, so we know that our function is going to be of this form. First of all, there could be a constant. We always have to assume there could be a constant. So I'm going to write that as a. In the numerator, because I had that one horizontal intercept at 3, 0, and it looked linear when it passed through, that's got to come from the factor. The factor must have been x minus 3, right? To the 1 power, but we never write the 1 power. And then the denominator is going to give me the vertical asymptotes. So remember we had a vertical asymptote at x equals -3. So that must have come from the factor x plus 3. And it's to the 1 power again because as you approach from the left and when you approach from the right, the function went in opposite directions, right? In one case it went to negative infinity, the other case it went to positive infinity. So that's why we have a 1 there. Again, I don't write the 1. And then the other vertical asymptote was x equals 4. So that came from the factor in the denominator of x minus 4. So actually, we're almost there. We almost have the exact function that we want. We just need to figure out a. So how do we figure out a? We plug in a point that's definitely on the graph and we can solve it for a. And usually the easiest point to plug in is probably going to be the vertical intercept in this case. So I'm going to plug in the vertical intercept, which was at, what was it? It was 0, 1, right? It was 0, 1. So if my f of x is 1, my y is 1, and my x is 0. So I'm just putting in 0 in for x, anywhere I have an x. Then this is going to be, let's see, it'll be -3a over, and then 3 times -4 is -12. But -3 over -12 is 1/4 a. And then if you multiply both sides by 4, then we're going to have a is equal to 4. So the final answer then is going to be f of x is equal to 4 times x minus 3 over x plus 3 times x minus 4. So that would be the function, right? That's the actual equation of that graph. Okay, let's do a couple more of these. Here's another one. Okay, so here's the rational function, the graph of the rational function that we want to try and figure out what its equation is. All right, so let's think about this. Let me go to annotation again. Let's look at what we know. Okay, so first thing, I definitely have a vertical asymptote here at x equals -3. And I plotted in dash. Normally this won't be plotted here, so you're going to have to realize that there must be a vertical asymptote there. Actually, here, let's look at it if it wasn't plotted. Oh, I need to get out of this first. So if we didn't have that, right, it would look like this. And you would have to realize, oh yeah, there's definitely a vertical asymptote there at x equals -3. Because one side is approaching infinity, the other side's approaching minus infinity. Anytime they're approaching infinity or negative infinity, there's some type of vertical asymptote. But I put it in there just to make it more clear. So x equals -3. And let's change that color to blue. Okay. So now, let me go to annotate again. So there's a vertical asymptote, asymptote at x equals -3, or x equals -3 is the vertical line. That is the vertical asymptote. And what factor does that come from? It comes from the factor x plus 3, right? And what is the exponent? Here, I'll write it. This comes from x plus 3. And because one side is going to positive infinity, the other side is going to negative infinity, right? They're going opposite directions. That factor, the exponent there is a 1. And this factor is going to be in the denominator, right? Because when we're talking about vertical asymptotes, it's where the denominator is equal to 0, when it's undefined, or the denominator is equal to 0. Okay, so that's 1. Now let's look at the other vertical asymptote. It looks like it's at x equals 4. So that comes from the factor x minus 4, which has to be in the denominator. And again, what is the exponent? Well, I guess it's 1 again, right? Because this side, as I approach 4 from the left, the function is going to positive infinity. As I approach 4 from the right, it's going to negative infinity. So they're going opposite directions, so that must be a 1. All right, let's look at intercepts now. So vertical intercept. Where does the graph cross the y-axis? Well, actually, it looks like right in the origin, right? So the origin in this case, so 0, 0 is going to be a vertical intercept. And then how about horizontal intercepts? Looks like I have 2 of them, right? Actually, 0, 0 is again a horizontal intercept because that's where it's crossing the x-axis. And also, I guess, 3, 0. So, and 3, 0. Now, where do those come from, the horizontal intercepts? Well, they come from the factor x minus 0, but you never write x minus 0, you just call that x. So it comes from x, and that's to the 1 power. How do I know that? Because very close to this horizontal intercept, if you were to zoom in, it looks like a line going through, right? So it's going to be a 1 power. And the other one comes from the factor x minus 3, right? Because if I set x minus 3 to 0, that's how I get x equals 3. And again, it looks like a line going through. If you zoom in closely on this, it looks just like a line going through. So that factor has to be a 1. And then finally, it looks like there's also a horizontal asymptote. Let's see, as x gets really, really big, so as x gets really, really large or really, really small, it looks like the function is approaching -2, right? So I have a horizontal asymptote, and that line is going to be y equals -2. Okay, so we're going to use all that information to come up with the actual function. All right. So the question is, remember, in general, there could be a constant out front, which we're going to call a. So how are we going to determine that a? It turns out that we could do it just by looking at the horizontal asymptote, and I'll explain that in a second when I go back to the iPad. The other way of doing it is, again, just plugging in a point, but I can't use any of these points right here because they'll just, it'll be 0 times a, it won't allow me to find a. So I have to pick a point that will allow me to find a. And if you look on here, it's not obvious, but it looks like this one is exact. And if I click on the, oops, let me get rid of this annotation. If I click on the graph there, that point is -4, -7. So that I know is a point that lies on the graph. So I could use that point -4, -7. So let me note that in here. So I'll put it over here. So -4, -7 lies on the graph. Because we might need that to figure out the a later. But we could also do it from the horizontal asymptote, and I'll explain that. in a minute. Okay, you guys have that? So let's go back to the iPad. Okay, so we're trying to figure out the equation for that function of that graph that we just saw. And remember, we found several things. We found that there was vertical asymptotes at x equals -3, or that was the line x equals -3 and x equals 4. We had a horizontal asymptote. So vertical asymptote, horizontal asymptote, and that was y equals -2. We had a vertical intercept, right, where it crossed the y-axis. That was at the origin at 0, 0. And we had a horizontal intercepts, two of them, one at 0, 0, and also at 3, 0. Okay, so let's put this all together. So we have f of x equals, well, there could, again, could be some constant a out front. Now, how do I get the numerators? Well, remember, the numerators come from the horizontal intercepts, right? If this is basically saying x equals 0 and x equals 3, those are my two zeros or my two roots. So the horizontal intercepts are 0, 0, and then 3, 0. So that means the factors that gave rise to those roots must have been x minus 0, but I just write that as x. And then the other one is x minus 3. And they both have exponents of 1. Why? Because the graph looked linear. It looked like a line when it passed through the horizontal intercepts. Okay, and then the factors in the denominator are going to lead to the vertical asymptotes. So if I have a vertical asymptote, right, of x equals -3, that means the factor that it came from must have been x plus 3. Again, how do I know that that's a 1 and not a 2 from an exponent? Because when we looked at the graph, as we approached x equals -3, one side went to -infinity, the other side went to +infinity. They went in opposite directions. So we know that we have a 1 as our exponent for that factor. And then what's the other factor? Well, the other vertical asymptote was x equals 4, the line x equals 4. So the other factor was x minus 4. And that again had to be a 1 because the graph went in opposite directions as it got closer and closer and closer to x equals 4. Okay, so great. So we're almost done. The only thing we need to do is figure out the a. So there's a couple of ways you could do this. Remember that we could use the horizontal asymptote because we haven't used that information yet. So we know that the horizontal asymptote is y is equal to -2. And remember, that deals with the long run behavior of the function. So this function, what does it look like for long run behavior? Well, it only depends on the ratio of the leading term of the numerator divided by the leading term of the denominator, right? In this case, the leading term of the numerator is going to be ax squared. That's the largest term. And what's the leading term of the denominator? It's just x squared. So in this case, right, the x squareds cancel. So the degree of the numerator is equal to the degree of the denominator. And this is just equal to a. Well, since it's equal to a, and we know that the long run behavior, right, as x approaches infinity or -infinity, is equal to a, then that a must be -2, right? Because the long run behavior tells us what the horizontal asymptote is. It's going to be that constant. So this tells us that a is equal to -2, right? And again, I got it from looking at the horizontal asymptote. If you don't like that argument, then we can just plug in a point. And remember, we found a point that lied on the graph. So here's the second way we can argue that. We can plug in that point. What was it again? -4, -7, right? -4, -7. So where I have my y, I'll put in -7, and an a, and then where I had an x, I'll put in -4. So it was -4, then it was what, x minus 3 over x plus 3, and then x minus 4. Okay, so a little bit of work to do here. Let's see. So -7 is equal to a. This is going to be -4 times what? Well, -4 minus 3 is -7. And then -4 plus 3 is -1 times -4 minus 4 is -8. So I guess this is 28, right? Positive 28a over 8. But then 28 over 8, I can simplify to, let's see, it looks like 4 goes into both, right? So 7 halves a. And then if I multiply both sides by 2/7, so this is gone, right? So I'm going to get a is equal to, well, the 7's cancel, and I get -2 over 1, which is -2. So again, I'm going to get -2. So you could either use the horizontal asymptote information to, realize that it has to be -2, or you could actually plug in a point, and again, you'll get -2. So my final answer is going to be, for that function, is f of x. It's going to be -2 times x minus 3 all over x plus 3 times x minus 4. Right, so that would be the function. Okay, let's do one last one. Okay, so here's the last rational function that we want to look at and see if we can come up with the actual equation for it. So if we look at this, right, it looks like, let me annotate this again. It looks like we have a vertical asymptote of x equals -3, right, that line. So vertical asymptote, and the line is x equals -3. So that comes from the factor x plus 3, right? Because if I set x plus 3 equal to 0 and solve it, I'm going to get x equals -3, which is in the denominator, right? Because it's a vertical asymptote. And what is the exponent on here? Well, because one side is approaching positive infinity, the other side's approaching negative infinity, it's just a 1, okay? I have another vertical asymptote. And that one is x, it looks like x equals 2. So that comes from a factor in the denominator of x minus 2. But what is the correct exponent for that factor in the denominator? Well, since both sides, as I approach 2 from the left and from the right, they're both going in the same direction. In this case, they happen to both be going towards negative infinity. That means that that factor in the denominator is squared. Right? Remember, if they go in opposite directions as you approach the line, it's a 1. If they go in the same direction, it's a 2. Okay, good. So that's vertical asymptotes. What about horizontal asymptotes? Well, as x gets really, really large or really, really small, what's happening to the function? It looks like it's approaching 0, right? So we have a horizontal asymptote of y equals 0. Okay, what about vertical intercepts? Where is it crossing the y-axis? Well, that looks like right here, and I guess it's -0.5, right? -0.5. So it's going to be 0, comma, -1/2. And then horizontal intercepts, it looks like there's only one, right? And it's right here. Let me click this off for a second. So it's right here, right at 1, 0. And if you zoom in on that, it looks like a parabola, right? It's approaching it and bouncing off. So it looks, if you get really close to that, it looks like a quadratic function of parabola. Okay, so what does that mean? Let me go back to text. Actually, I want to go back in this one. Wait, how do I do that? Oh, it doesn't matter. I can move this around. Okay, so we have a horizontal intercept at the point 1, comma 0. So where does that come from? It comes from a factor in the numerator of x minus 1. But because it looks like a parabola right near that 0, right near the horizontal intercept, what must the exponent be? It must be a 2, right? So it's got to be squared. Okay, and I guess that's all the information we have. So let's use all this information to figure out that function. So I'll go back to the iPad one last time. Okay, so let's figure out the function for that graph that we just observed. So again, what did we find? We found that there was vertical asymptotes, right? The line x equals -3 and x equals 2. They were both vertical asymptotes. There's a horizontal asymptote, and that was the line y equals 0. There's vertical intercepts, actually one vertical intercept at 0, -0.5. And then there was a horizontal intercept at 1, 0. Okay, so the function must look like this. Again, there could be an a, right? We'll have to figure out what the a is later. So in the numerator, that factor is associated with the horizontal intercepts, right? So if we had a horizontal intercept of 1, 0, that means the 0 or the root was x equals 1. That means the factor must have been x minus 1. And then to figure out the power, we had to look at what the graph did near that root. And it looked like a parabola, like it looked like a quadratic function. So that told us that this exponent must be a 2, right? And then in the denominator, the factors are associated with the vertical asymptotes. So if I have an x equals -3, if that's one of my vertical lines, vertical asymptotes, then the factor that gave rise to that must have been x plus 3. And since approaching that line from left side and right side, the function went in opposite directions. One went to positive infinity, the other one to negative infinity. Then I know that that factor is a 1, right? So I don't have to do anything else. And then my other vertical asymptote was x equals 2. So the factor that gave rise to that was x minus 2. But in this case, remember when we looked at the graph, they were both going towards negative infinity, right? They're both going in the same direction. So that means this exponent here, the power, was a 2. Great, so we almost have exactly the function that we need. We just have to figure out a. So let's plug in a point. Well, in this case, the easiest point to plug in is going to be the vertical intercept, right? Because we know it passes through the y-axis, that vertical intercept. So let's plug in that point. So I have negative a half, that's my y, is equal to a, and then the x was 0, right? So 0 minus 1 squared over 0 plus 3, 0 minus 2 squared. Okay, so negative a half equals, well, negative 1 squared is positive 1, right? So that's just a, over negative 2 squared is positive 4. Positive 4 times 3 is 12. And then if I multiply both sides by 12, we can simplify this. Right, that's going to cancel. Here I can simplify a little bit. I'm going to get a 6 up there. So I'm going to end up with a is equal to negative 6. So my final answer for that function is f of x. It's going to be negative 6, right? That's the a. Then it was x minus 1 squared. That was in the numerator. And the denominator was x plus 3 to the 1 power, so I don't have to write that. And then x minus 2, but that was squared. So that would be the function for that particular graph that we observed. All right, excellent. So that was a pretty long section there, 3.7, but that's the last section that we're gonna look at in chapter 3. And after this, so the next thing I'm gonna start is chapter 4, which is gonna be on exponential and log functions. Okay, and then after chapter, and that's pretty long. I think there's at least 6 sections in chapter 4. Then we'll do a little bit of trigonometry, maybe a little bit with vectors, and that'll be the end of the course by then. Great, thank you.